Okay, now let's talk about object detection. I remember that the goal of object detection is to find the location and the extent of the targeting objects. Like in this image, we want to detect all the faces. So the challenge for object detection using deep learning also started with producing high resolution output from those low resolution from those classification networks with aggressively downsampling. And the first solution proposed by Overfit is we can slide the network for classification on the whole image, and then for each image location at different scales, we can predict the bounding box location and the bounding box classification. This is very similar to the traditional sliding window approach. Basically, we treat this image classification as a classifier, just as one black box model like SVM, together with feature extractor, and then slide this object detector on the image at different location and at different scale. So later people find that we can actually do things in a more selective way. Say instead of sliding the network on the image exclusively, we can first propose the informative regions from the image and then crop those informative regions into the network to classify it. And the way we can propose the region is also start with the traditional methods. For example, we can segment the image with super pixels and then hierarchically aggregate those super pixels together in order to form the initial regions of possible objects. And of course, why don't we make that region proposal deep and using deep learning to learn how to propose informative regions, and that's what FastRCN is doing. So it proposes a region proposal network and use ROI pooling and anchors to extract region features. It means that we will first at each image location classify. We will put a set of anchors on each image. Those are virtual anchors. Basically, says that what if at this location the object is a square, or the object is a rectangle in different orientation, and then we will first classify that which anchor box it can be at this location, and we may have k anchor box, and usually those anchor box cover different aspect ratio and different scales. And at the same time, we also try to regress, say within this anchor box, what will be the refined coordinate of the object is, and then we will have those proposals at each anchor box. And remember that we have multiple anchor box at each pixel location. Then we can find that the most promising anchor box or the most promising proposals at each location. Then we put all the proposals together. So for further classification and regression to refine the object location, and also trying to see that whether the object, what will be the classification, exact category of the targeting objects within this anchor. And to represent those proposals, we have reason ROI pooling, basically based on the bounding box proposed by each anchor. Then we will resample the feature from the convolutional feature map to form the representation for that proposal. And that was so as you can see, FastRCN put the detection problem into two stages. First, we propose the likely object regions, and then do another further classify. So usually that multi-stage network is slower because you have multiple parts. And there is another proposal of network design. It's called YOLO. So it's short for you only look at once. So the goal here is to have a real-time object detection. And the idea here is instead of first propose the regions and then classify, can we do join both proposal and classify at the same time so that we can potentially reduce the total computation needed. And to achieve that, say at the output layer, we classify each like a big block or each pixel in the downsampled feature map to see that whether it's what will be the category of the target object. Let's say this this pixel may be on a bicycle, or this pixel is on a dog, and then we have a separate branch to regress the extent of this object. And in the end, we can use non-maximum suppression to find out that what is the most likely bounding box for the target objects. And another way of refining the detection is using feature pyramid network. So this can be used together with faster RCN. And remember that faster RCN is still using the traditional classification network as its backbone to extract the features, but that will also that may miss some small objects. So feature pyramid, the proposal of feature pyramid, very similar to a fully convolutional network, and it's trying to re-aggregate the information from higher level to a lower level to have a feature map that is higher resolution but contains semantic information. And what if we want to segment the object, not just to detect the objects? So the problem itself called instance segmentation. And the current popular method is called master RCN. So it's built based on faster RCN, and its extent is build a new branch based on faster RCN. So basically, in faster RCN, for each region proposal, we will pull the feature from the original convolution network and pull them together so that we can have a one-dimensional representation for that region. And then for that region, we can do classification to understand the object category and also regress the extent of the object. But here for mass RCN is built on that idea, and instead of doing ROI pooling, is doing ROI align to extract not just one-dimensional feature map, but to extract not one-dimensional feature representation, but to extract a feature map for that potential object, and then we can learn how to segment within this feature map. And ROI align is an extension of ROI pooling. So basically, it's a better way of finding a feature representation for the potential object and make that feature representation into a feature map. So this is an illustration of ROI align. So the blue box are the are the feature locations in the convolution map, and this black box is the predicted region of the is the potential region of the target object, and we want to have feature representation on each location in this feature map. And what we can do here is so we can basically do interpolation of nearby features for each location on this on this new feature map. So usually we predefine the feature map dimension. Say we can make it 7 by 7 or 16 by 16, and then for each location on this pooled feature, we will try to sample from the original feature map to interpolate the feature map and then find a feature representation for each location on this map. And the result of master RCN is very good. So you can see it can detect the objects just like a fast RCN, and at the same time to segment the underlying objects behind this bounding box. And there are also some shortcomings. For example, if we are considering some very large objects or with finer boundary or small structure, just like what we observe in FCN, it can get some blurred boundaries. And another way to get a finer information from those detected objects is post-estimation. Here, instead of finding the segmentation of the detected object, we want to find the key points and the key point and the skeleton of the targeting object. And here we are mainly detecting the pose for human. So for human, we can define the pose in several ways. And in a recent paper called dense pose, they try to densely locate the key points on the human body instead of extracting only the skeleton. And we can segment different body parts and also locate the key points on each part. So the solution is actually very similar to mask RCN. So we can still use RLine to extract the feature map for the detected object. And then on the feature map, instead of only segmenting the foreground and background to find the target object, we can do a multi-way classification to find the different parts of the objects. And we can make this also make this multi-head. So one branch of this head is used to segment the objects to find different parts, and another head can be used to find key points on the object, and those two things can be merged together so that they can help each other and find consistent key point detection and key part segmentation. So as you can see here, with the basic structure of fast RCN, we can do instant segmentation as well as post detection. And if you want to do this yourself, there are several open source packages you can directly use. And one thing that is commonly used in research is called Detection Tool. It's released by Facebook. So it's kind of an official implementation of fast RCN, mask RCN, and also post detection. Okay, so what if we are not happy with only pixel information, and we want to predict some geometry information from the image? We can also use a similar technique and use deep learning methods to achieve that. So here, let's consider 3D object detection, which means that we not only want to find the object location, but also estimate their 3D locations. And again, so we can parameterize the 3D location of the objects by its dimension and the view angle, and also depth. So just similar to how we do like image classification from the convolution features, we can directly use those information like depth, dimension, and the view angle as a supervision signal, and to learn how we can predict those information. And you can see that with this simple method based on convolutional networks, we can predict the dimension and the location of the object pretty accurately. So now let's talk about how we can go from image analysis to video analysis. Basically, we want to understand that how we can not just locate objects, but also track the object in temporal domain. And the object tracking has been divided into detection and association in the current major paradigm. So we have talked about how we can build the feature representation for each location on the image, and how we can convert that feature representation into object detection network. And for tracking, we are mainly concerned with how we can do association, how we can associate detect objects across frames together to find the bounding box of the same objects, even though they will have some perspective change and some perspective distortion on the on the images. So, and one thing is we are basically trying to resolve a matching problem. So we have different matching candidates on two frames, and then our goal here is to figure out that on this bipartite matching, which connection is the real, which matching is the fake connection. It's worth noting that the similarity or the connection between each node can come from multiple sources of information, not just from, say, appearance similarity. It may also from some motion pairs or even social constraints. And to solve this assignment problem, we can turn to Hungarian algorithm. It's a classic combinatorial optimization algorithm to solve this kind of assignment problem. Basically, we have two sides and we have a cost between each assignment, and we want to optimize a unique assignment for each person, say, to the tasks. And to learn feature similarity, we have two ways of doing that. One way is, say, we do a binary supervision signal. Given the tracking labels, we can say that whether these two boxes are the same and these two boxes are not the same. Then we can use this signal to pass into a two-way classification to learn the metric of measuring whether the two objects are the same. Or another way is we can use triplet loss, which is not only considering a pair of objects. We say that instead of saying these two are the same, we say that these two are more similar than this pair. It's also another popular way of learning similarity. And if we use this type of methods, we can get a very decent results, and it has been used in a lot of systems. However, as people have observed, this type of method does not really use a lot of information from the association. Majority of the performance come from, say, motion pairs and other tricks. And therefore, people have studied how we can fully utilize the power of deep learning to do tracking. And one way of doing that is using this directly regress the location of the objects from the previous frame to the current frame. So, for example, we can have the target from the previous frame feed to a network, and then on the new frame we can crop a search region. Say we assume the object does not move beyond 100 pixels, and pass this search region into another convolutional network to build representation for both the search region and the target region. Then we can merge these two together to regress the location of the targets within the search region. And we can even pre-train this network on a large amount of video data set. And even beyond this, simply regress the location of the objects. We can first build a correlation features. Basically says that instead of predicting a regress location directly, let's blend in some additional information. First, find the correlation of the different location between different locations of the feature map, and then use that added information to predict that where the object can move from the first node to the next. And here is an illustration. So those are the feature map that we see from the convolution networks on each individual frames, and we can build a convolution, build a correlation. You can see the correlation response can extract the um, displacement of the target objects from across different frames very effectively, and then we can use another network to decode this correlation information to predict that where the object is moving across the frames. And then after have this prediction, we can do association, just comparing that which detection is close to this prediction. And we can even do this, push this even further, just not even looking at the future frames. Then we can directly regress the possible location of the bounding box, and then see that where it can be in the next frame. And after that, we look at the next frame to see that whether our prediction is correct, or try to associate our prediction with the newly detected bounding box. So recent work has discarded measuring similarity between bounding boxes directly. Instead, they are using regression to predict the object location in the next frame, and then use the predict box to associate with the detected box just based on location. And it's mainly because similarity doesn't seem to provide appearance similarity does not provide us much information. And this is very weird. So let's try to understand why it's the case. So first of all, on this two image, say we only have two bounding box, and then we can use this pair of connection to supervise our similarity and appearance network to find out and build a measure to measure the similarity of appearance. So the problem of this comparison in the traditional work is it discusses much of the regions, many regions within the image. For example, if I shift this ground truth bounding box a little bit, will that have a very high association score with the other box in the next image. Also, there may be a lot of confuser or hard negatives on the background that are not considered in this framework, in this way of comparing similarity. So instead, we can use a coincidence similarity learning. The idea here is we can, instead of comparing only the detected bounding box from between two images, we can actually compare the proposed bounding box from two images, basically trying to find all the informative regions between a pair of image, and then build connections between them and learn from those connections. This can be naturally integrated with the faster RCNN framework. So we can extract those informative regions from the region proposal network, and then send them to the embedding head to extract the features, and then learn the connection and similarity and dissimilarity between those proposals. And you can see that with this simple way of measuring similarity, and it actually become very effective. So we can use only appearance similarity without the other bells and whistles to track objects and achieve much better performance compared to the previous methods. Now let's consider 3D object tracking. It's similar to the definition of previous task. In 3D object tracking, from binocular videos, we want to detect the located objects, track them across frames, and also find their 3D location at each frame. So because of this definition, we can actually build the solution based on the previous methods, especially fast RCN. So we can still, given an input image, extract the region proposals, and for each potential object candidate, we can estimate its depth, center, and dimension. And when we have a different frame, we can associate them together. And when we have even more frames, we can find a better 3D trajectories for the objects just by analyzing its motion. And again, here we can use FastRCN as a base building block to locate objects and find the information for each region and build the representation for each object. So one thing here is what will be the center of the objects? How do we find that on the image? It turns out that the center of the 3D objects is usually not projected to the center of the 2D detected bounding box. If the object is fully observed, then the distance between the 2D center and the projection of 3D center may be very close. But when the object is occluded or truncated, then the center of the detected box will be very far away from the 3D projection of a 3D bounding box. Therefore, we can predict the 2D location as well as the projection of the 3D center from the features extracted for each proposal. And here, for each after we have the feature of a proposal, we can also predict the dimension, orientation, and the depth of the object. And with those information, we can reproject the detected 2D object into 3D. When we have multiple frames, we can connect the different frames together and use an LSTM to learn the possible object motion, and at the inference time, use LSTM to correct the motion of the object. This is very similar to a common filter. So in summary, for all the supervised recognition tasks in computer vision, you can basically find a bucket of computer vision convolutional networks as the solutions. And basically, we are using fully convolutional networks to find the pixel-wise representation for the pixel-wise prediction task, like segmentation and boundary prediction. And if you want to have instance level information, we can use FastRCN to extract the possible regions and then further classify the property of the region. Either is object level information like the extent of objects, or even finer information like the segmentation of the objects or the pose of that object. Of course, there are also a lot of other solutions. So in the literature, trying to solve those tasks better, but those are the basic building blocks for the current methods.